So just want to get that out of the way. And without further ado, I will hand it over to Laura.
All right, thank you so much for the introduction. And I gotta say, I was had a speech at RFO planned twice during the pandemic that got canceled both times because of changing conditions with COVID. So I'm just overjoyed to actually be able to come and speak. And if any of you, especially local people, have not been up to the observatory, I cannot recommend it more highly. It's just such a fantastic time. Please, please, please go up there and check it out. All right, so I'm going to go ahead and share my screen. Let me get my slideshow going here. See. So when I was asked to speak for Women's History Month at RFO, I sort of went back and forth about which women I should highlight and what I should talk about. And I ultimately decided I'm just going to pick the 3 women who have inspired me the most personally. So that is the unifying theme tonight. I wanted to just share with you some history of Henrietta Swan Leavitt, Vera Rubin, and Kathy Vivas, 3 female astronomers who have just made absolutely amazing contributions to the field that have really inspired me personally. All right, so Henrietta Swan Leavitt is a famous astronomer who discovered something called Cepheid variable stars. Now, I'll talk more about what those are in a few moments, but just for now, they're special stars that grow and shrink and actually get brighter and dimmer. And if you know exactly where to look and you know where to find these stars, you can see them getting brighter and dimmer over the course of just a few days. And I'll even show you one that you can go out and see tonight if you're interested. So she discovered a ton of these Cepheid variable stars. She studied almost 2,000 variable stars, some of which were these special, really important special kind called Cepheid variables, in these little galaxies that are right next to the Milky Way called the Magellanic Clouds. So I'm going to talk about what, why it was important, what she learned, how completely revolutionary it was in changing our understanding of the universe. And I'd also like to talk a little bit about the background of how she became an astronomer. So in the 1800s, in the early mid 1800s, this new technology had been invented called photography. And here's one of the earliest photographs that had people in them. You can see the little people down here kind of walking around. There was a famous portrait of Abraham Lincoln taken in 1857. Photography was getting better and better. And eventually, people were able to take cameras, attach them to telescopes, and take pictures of astronomy objects. Now, at first, the pictures were not very good. This was a picture, the very first photograph taken, I believe, of the Orion Nebula, taken by Henry Draper in 1880. Now, if you don't know about the Orion Nebula, if you can go outside and find Orion's belt, which are 3 famous stars in the sky, just below Orion's belt, there's a kind of faint fuzzy patch in the sky, and that is a huge nebula where new stars are being born, like a nursery of new stars. So this picture doesn't really do it justice, and that was in 1880. Well, photography was rapidly getting better and better. The technology was improving. So here's a picture of the Orion Nebula taken in 1888 at Harvard Observatory. So here's the nebula down here, just below Orion's belt. So things were getting better and better. And this created a huge shift in how the work of astronomy was done. Oh, I forgot, I have a great picture of the Tarantula Nebula. Actually, I was just going through some of the early pictures from Harvard University Observatory, and this, I'm sure this picture is long dead and gone, but been immortalized in the astronomy archives at Harvard. All right, anyway, how astronomy was done. It used to be that people would have to look through the telescope, like sit there with their eye on an eyepiece and draw out what they were seeing and draw out where the stars were located and how bright they were. Well, photography changed all of that because now you could just snap photographs of portions of the sky. You didn't need a person to map the sky anymore. You can detect brightnesses are not the same every night. A lot of them get brighter or dimmer as time goes on. And it takes a lot of skill to be able to a star getting a little bit brighter, a little bit fainter with the naked eye. I would be astonished if any of you have ever discovered a variable star just by looking at it in the night sky. It's really difficult. But with photography, it's pretty easy because you can take pictures of the same stars night after night and then just compare the photos and see if the stars are changing. And spectroscopy, this is when you take a prism and split all of the color ingredients that make up that light. You can take a photograph of that rainbow and then be able to learn all kinds of interesting things about the stars from that photograph. So Williamina Fleming, who was a woman who worked at Harvard Observatory in the late 1800s, early 1900s, said you can obtain in one night represent years labor observation, meaning now that we've got cameras, this is just a complete game changer. It changes everything about how we do astronomy. So this opened the door for women to get more involved in astronomy in a way that they never had been afforded that opportunity in the past. There's also a lot of sexism involved in the choice to employ women to do astronomical work in the late 1800s. So I wanted to share with you, as I was researching for this talk, I did some reading and really dug through some old articles and like what were people thinking about back then in the early 1900s about how women could participate in astronomy. And I found this kind of condescending quote: women prove themselves more competent than men in work requiring care, infinite care and detail. They are more painstaking, more enthusiastic, less apt to grow tired in meticulous, exacting labor than are the men. Kind of makes you think of like, well, you should do the dishes because you're less apt to grow tired at that sort of task because you're a woman. But this was the way people thought back then. And so they thought that now that there were all of these, hundreds of thousands of photographs of nebulas and stars, they needed people to go through all those photos and analyze the data. There was just so much data coming from photography that hadn't been like that before. There wasn't so much data to go through prior to photography really taking off. So they decided that it was okay to employ women to do some of the detail work involved with analyzing all these photos and trying to make sense of the new data they're getting about the stars. Another quote that I found that was really interesting to me. The intelligence women have in astronomy has only been a larger expression of the power that made them able housekeepers and homemakers. And women aren't rivals of men, but they often suggested and planned the work of men, thus fulfilling their mission in the scheme of creation as helpmeets. Okay, I'm a little skeptical of the reasoning on this, but those attitudes did sort of, in a weird way, open the door for women to participate in astronomy in a meaningful way. So let's talk about, how women got involved. There was a guy named Henry Draper who he died in 1882, and his wife donated all of the money to a group called the Henry Draper Memorial. Now, she was a real astronomy enthusiast. She wanted the work of Henry Draper. Henry Draper was basically a photographer who took a lot of pictures of astronomical objects. So she wanted to basically fund a group that would continue his work, that would carry on the work of her husband who had passed away. And since she was a woman, she wanted to empower women to get involved in astronomy. So it seemed like kind of a good fit to hire women. The other thing was you could hire really qualified women because there was the Ivy League of all these prestigious colleges in New England and on the East Coast, but then there was also the 7 companion schools for women where women were getting degrees in astronomy. They were studying astronomy in college, graduating with all the same qualifications that men had, but there were basically no opportunities for them. So you could hire women for $10.50 a week to do this work. And it's really pretty skilled work. Compare that to at the same time, the standard pay for school teachers, like elementary school teachers, another job that women commonly occupied, was $10 to $20 per week. So you could hire these really skilled like astronomers who had been trained at top-notch institutions for the same wage that we would be paid to like an elementary school teacher at the time. So it was a pretty good deal because you certainly couldn't hire the men for that rate. It was a good deal for the observatory. The women were called computers. They computed things, so they were called the Harvard computers. And here's a photograph of the Harvard computers with, I cannot, for my whole life, I will never get over what a ridiculous haircut this guy has. Edward Pickering, the leader of the group of women at Harvard Observatory. And then here are all these women that he hired to do the detailed work. Now, this is a photograph of them working, basically looking at photography plates, making notes on them, annotating. This woman been able to figure out what she's looking at or what she's doing. And they all just seem so occupied. It really reminded me when I was a college student at Arizona State University, there were not very many women in my program. There were maybe like 3 or 4 women in my graduating class for my physics degree. And anytime they needed pictures for the college website, I always ended up in them. They would like come and ask me to pose or like hold a screwdriver or like look into a microscope or just something. And they would take pictures of me. And I can't help but think that that's what happened here. They're like, okay, everybody look through a magnifying glass, look through that tube, look busy, we're going to take a photograph. It just seems a little too perfect. So it always kind of cracks me up. It's kind of a famous picture. Okay, so let's get on to what Henrietta Swan Leavitt, who's just one of these, if you're interested in this, there are a ton of amazing women who worked here. Annie Jump Cannon, Cecilia Payne-Kaposhkin, Henrietta Swan Leavitt is just one of these amazing women. I'm just going to her. What did she research? See, you can go outside, look low in the north, like look towards the northern horizon, and you'll see a constellation that's sort of shaped like a child's drawing of a house. There's the pointy roof, there's the house part, the door would be right here. And on the bottom left of the house, there's a little isosceles triangle. And the point of that triangle is a famous star called Delta Cephei. Now, what's special about this star is it's one of those, actually all Cepheid variable stars are named after this star, because this is the most famous of that type of star. It's a star that it grows and shrinks and changes its brightness as it does that. So I don't know if you can tell on my screen, but one of the stars in this little triangle is a little bit brighter and the other one's a little fainter. And what's really nice about this is the point of the triangle actually varies from looking like this star to looking like this star. It actually changes over the course of about 5 days. So even without good equipment, you can go out and actually, if you watch it for 5 nights in a row, you'll see it change, which is pretty neat. If you have any trees though, you're probably out of luck right now because it's so low in the sky that any like trees or buildings will mess it up. But if you get up at 4 in the morning, it'll be up high in the north, a little bit higher in the northeast. So you can go out and see this thing tonight if you want to. Now, in this picture, these 2 pictures, there's one difference. The left picture and the right picture are not identical. There's actually a star that's so bright in the left picture that it's like a big old bright star. And in the right picture, you can't even see it because it's so faint. I'd be really impressed if any of you could find the difference yet. But I wanted to show you some technology that makes it a little bit easier. If you take 2 pictures and then look at them in the same place moment by moment, isn't that a little easier to find that star that changed, right? So one of the ways that people would discover variable stars is to do this. You'd take 2 photography panes or 2 photographs, put them one on top of the other, and then kind of move one out of the way. There's a machine called a blink comparator where you could actually use a foot pedal on the ground and hit it, and it would move one of the pictures out of the way and let you look at the other, and you'd see this star kind of winking in and out of existence. So that's one of the techniques that Henrietta Swan Leavitt used to discover these changing special stars. Another thing she did is she would take one photograph of an area of the sky taken one night, and then a few nights later she'd have another photograph of the same stars, but she'd get it developed like in negative format, like where all the stars look like dark spots and the space behind it looks like bright spots. And then when you put one of those on top of the other, it should all just be black unless there's some change. And so she'd be able to notice changes in the sky that way. So over the course of her years studying variable stars, she located and discovered hundreds, almost 2,000 stars, variable stars in the Large Magellanic Cloud. This is just a photograph of some stars, but then every single one of these little scribbles is a line marking a particular star, and then some numbers kind of labeling the star and how bright it is. All of those stars are things that Henrietta Swan Leavitt studied, and she made all these markings on the photograph. So that's just something to keep in mind, like the detail work that was involved just for one picture of finding all of these different variable stars. So I haven't told you yet why the heck you should care about Cepheid variables. So let me tell you. They are basically signposts that let you measure how far away things are in the universe. And let me go through the basic idea of how it works. Don't worry, I won't get too technical, but just a little bit of science here. So in general, Cepheid variables grow and shrink. And if they are really big, giant stars, then they're pretty slow to do that. Like, just like it takes, it's a little slower for a semi-truck to turn compared to a bicycle. You can turn pretty quick. Big, huge stars, it takes them a while once they grow and get really big to turn around and shrink back down. So large Cepheid variable stars tend to pulse in and out. And what that looks to us from Earth is just a star getting brighter and dimmer over the course of a few days. It takes them a while to do that. If a Cepheid variable is really small, then it actually will grow and shrink really quickly, like in just a couple of days. So slow stars are big, fast pulsing stars are small when we're talking about this one particular category of stars. So if you want to tell how far away a Cepheid variable star is from Earth, there's a pretty straightforward method to do it. First, you just time the star. You watch it night by night. You measure how long it takes to complete one cycle of growing and shrinking back down. If you've got a camera, it's even easier. You just take a picture of it each night, and then you look at the photos and you see how long it takes to brighten up and then go back to normal. If it's really slow and it takes a long time, like if it takes 10 days or something like that, or 30 days, you're dealing with a big monster star. If the whole thing's over and done with in 3 days, then you're dealing with a really comparably smaller star. Now, stars look, in general, when stars are bigger, they look brighter. So if you see a star that's really slow to pulse in and out, then that means it must be a big, bright monster of a star. Now, what if you time a star and it's really slow, it takes a long time, but then it looks super dim in the sky, like you can barely even see it, even through a telescope? Doesn't that mean it's really far away? If you're timing this thing and it's slow and you know that it's got to be a monster and yet you can barely see it, that means it's got to be so far. The farther away a star is in general, the dimmer it's going to look. So if you find a star like that, you can locate not just how far away the star is from Earth, but you can use it to tell how far the galaxy is that the star is a part of. So the real value to us of these Cepheid variable stars is they let us measure where giant groupings of stars called galaxies, it lets us measure where those are. And that lets us map out the universe and map out how matter fills the universe and where there are big empty voids and how large those are. So Cepheids are like signposts that let us, I kind of think of it like when you go to the driving range or you go golfing and they've got these little signs like 100 yards, 200 yards, 300 yards. You don't really care how far those signs are. That's not inherently interesting. You want to know how far did you hit your golf ball. But if the golf ball lands next to one of those signs, then you know, oh, I hit my golf ball 150 yards. Well, Cepheids are kind of the same way. They kind of shout out this message to us about how far away they are, and then that lets us tell how close or far away the object that they're located inside of, like a galaxy, is from planet Earth. Now, Henrietta Swan Leavitt discovered these stars. She studied hundreds of them, and she knew that they could be used this way. She knew that they could be used as signposts to measure distance, and that was a big deal at the time because they did not have a lot of good methods for telling how far away things were. But she was not really allowed to pursue any research based on this tool that she herself had developed. There's a great book you can read if you're interested about this called Miss Leavitt's Stars. And the author puts it this way: Henrietta Leavitt didn't get to pursue the matter herself. Pickering, that's the boss with the crazy haircut, kept her tied down with other projects. He wasn't one to encourage theorizing. In other words, he thought that the women's job at the observatory was to deal with the pictures. Like, okay, you got these pictures, we want you to analyze them, want you to write down all the stars you see, make lists. Your job is not really to think about all of this. Your job is to do the detail work. So it's this kind of patronizing, patriarchal attitude that we need to leave the heavy work of thinking to the men. So unfortunately, she did not really get to pursue all of the discoveries that could have come from the work that she was doing. But she did enable some amazing discoveries. So as I said, photography just kept getting better and better in the late 1800s, early 1900s. And by like the 1990s, they were getting amazing photographs of what we now know are, but what they called at the time, either spiral nebulae or just nebulae. They thought there were these like little gas clouds within the Milky Way. So here's a really impressive 60-inch in diameter, even bigger than what you've got at RFO, reflecting telescope north of Pasadena and Mount Wilson. And here's a giant camera that they would attach to the back of the telescope. So here's a picture of what they called at the time a spiral nebula. And they thought, to be clear about just for those of you who are maybe new to astronomy, the Milky Way galaxy is the galaxy, and there's about 100 billion stars in the Milky Way, and the sun is just one of those. But there's also 100 billion other galaxies in the observable universe. Now, at the time in the 20s, they didn't know that. They saw these little things, and we know today that this is actually a picture of a galaxy that has millions or maybe even billions of stars in it. But at the time, they thought that it was maybe just a cloud of gas that was inside of how far away it was. Here's another, they called it at the time a spiral nebula. We now know it's a spiral galaxy. But they thought maybe this is a twirly little nebula inside of the Milky Way. So the question was, are these spiral nebulae inside or outside of the Milky Way galaxy? The field, like the progression of photography had allowed astronomers to get all these pictures of nebulae, so called at the time, and they didn't know where they were. Are they in the Milky Way? This is our galaxy, the Milky Way, or were they way outside of the Milky Way? Well, luckily for astronomers at the time, the work of Henrietta Swan Leavitt paved the way to be able to answer that question. So here's a photograph of what we now call the Andromeda galaxy. They called it just Andromeda or the Andromeda Nebula at the time. And this is a photographic plate with notes written on it by Edwin Hubble. You might have heard of Hubble because of the Hubble Space Telescope. He's really made immortal by the naming of that telescope after him. But anyway, up here on the photograph, he found a star that seemed to be changing over time. So he labeled it VAR with an exclamation point, which means variable star. And the exclamation point is there because he knew that since it was a Cepheid variable, he could use this signpost technique that Henrietta Swan Leavitt had developed to measure how far away that was. At the time, nobody knew where Andromeda was. They didn't know, was it inside the Milky Way? Was it outside? So this was going to answer the question. And he knew that, and he was really excited. So he put an exclamation point and he wrote in red. So at the time, he measured that it was about 900,000 light years away. We now know it's actually more like 2 million. There was an error with, there's basically two kinds of Cepheid variables, and he didn't know that. So they used the wrong kind and it kind of mixed up. But anyway, even with the slightly wrong number, he came up with 900,000 light years, which is definitely not inside of the Milky Way. It's way too far away. Milky Way is about 100,000 light years across. So this is at least 9 times farther, and we now know it's even farther than that. So that was just a complete seismic shift in our understanding of how large the universe was, because not only was Andromeda outside of our galaxy, all these dozens of other spiral nebulae that they'd taken photographs of, that meant that all of them were outside of the Milky Way as well. In fact, they started calling them island universes, which I love that name. It's just so romantic, island universe. So this completely changed our view of how large the universe was forever. And it was all based on the work of Henrietta Swan Leavitt developing this famous discovery called the period luminosity relation, the idea that you can use Cepheid variables to measure distance. So you've all probably heard of the Hubble Space Telescope, but my little rebellion, my internal rebellion is, I call it to myself, just the Henrietta Swan Telescope, because I want to honor the work that she did that enabled these amazing discoveries later on. And I think if she had been encouraged, it's possible she might have gone on to make some of these discoveries herself. Okay, so that takes me to the second really inspirational woman that I wanted to talk about today, who is Vera Rubin. So Henrietta Swan Leavitt passed away in 1921. 7 years later, Vera Rubin was born in 1928. She studied something called galactic rotation curves, which sounds really technical, but it's extremely exciting because it was instrumental in the discovery of dark matter, this incredible invisible material. We still don't know what it's made of to this day, but it seems to fill the universe. There seems to be about 6 times more dark matter spread throughout galaxies than there is regular normal matter. And Vera Rubin discovered some of the first and most compelling evidence for the existence of dark matter. Now, I wanted to talk a little bit about her attitude towards science and sort of her experience of being an astronomer as a woman in the 60s and the 70s. I love this quote directly from her. This is not me, I don't live and work, these aren't my assumptions, these are Vera Rubin's assumptions. I live and work with 3 basic assumptions. There is no problem in science that can be solved by a man that cannot be solved by a woman. I agree with that. 2, worldwide, half of all the brains are in women. And 3, we all need permission to do science. And I think what she means by that is that science is such a huge endeavor, especially astronomy, that you need the cooperation of institutions and the resources and the equipment that goes along with it in order to do astronomy. I don't think people need permission to do experiments in science on a small scale, but to do large astronomical projects, you have to have the support of society in order to do that. So we all need permission to do science, but for reasons that are deeply ingrained in history, this permission is more often given to men than to women. And that was certainly true in the 60s and the 70s, and to some extent, it's still true today. She told a story that really resonated with me about an interaction she had with her high school teacher. She was in a class that was, I think, mostly male students. The high school physics teacher was like really an interesting guy, and he would always be doing experiments, demonstrations, and blowing things up and just doing all kinds of fun stuff. And all the students loved him. But she was just sort of more quiet in class. She didn't feel, I guess, 100% comfortable. I mean, I don't know exactly why, but apparently she never really spoke to him very much, and she didn't think he had much of an idea of what she was all about, or that she had this tremendous interest in astronomy that she had had since she was a young child. So she said, I really don't think he knew how to relate to a young girl in his class. And eventually she earned a scholarship to study astronomy at Vassar College, which she was just overjoyed about. And she told him she got the scholarship to Vassar, and he said, he didn't know what an interest she had in astronomy. And he said, well, as long as you stay away from science, you should do okay. It takes, as she put it perfectly, it takes an enormous self-esteem to listen to things like that and not be demolished. So rather than teaching little girls physics, you have to teach them that they can learn anything that they want to. And that don't let somebody tell you, yeah, you got to stay away from science. Just total garbage. And we need to teach young women to ignore any kind of barriers that anybody tries to put up in front of them around things like this. Vera Rubin was really supportive of other women and has helped pass the torch on to future generations of women. She's advocated and mentored other women. She was sort of famous for pestering astronomy conference organizers. It would be pretty common for an astronomy conference to get put together where there was no women anywhere on the agenda. It was just all male speakers. And if she ever saw that, she'd call him up on the phone and tell him, you know, we've got a problem and you need to fix it. And she was not shy about that, which made a huge difference in making space for women to participate. All 4 of her children went on to receive PhDs in science, and she had 3 sons and 1 daughter. And her daughter became an astronomer. This story kind of resonated with me too. She got her PhD in cosmic ray physics, said she was the only woman at a conference the daughter went to. And this was about 25 years ago that Vera Rubin said this, but she said she couldn't tell the story for a long time because not an awful lot has changed. Some things are better, but not enough things. I think that things are changing now, but it's still, I still agree it's not enough things, but things are substantially improving, I think, like in the last few years. So one thing I wanted to note is, as I was preparing for this talk, I found this really interesting that in the first woman I highlighted, Henrietta Swan Leavitt, she did this sort of like background work that made the discoveries of men possible in the future. Edwin Hubble was able to make discoveries on the basically standing on the shoulders of Henrietta Swan Leavitt. But Vera Rubin kind of turns it around. She actually gets all the glory and makes these amazing discoveries based on the work of men. So it kind of turns it around, and I thought that was sort of interesting. There was a really famous astronomer, kind of an eccentric guy called named Fritz Zwicky, who first sort of was one of the first people to propose the idea of dark matter in the 30s. He didn't have, the evidence that he had was not super compelling at the time. There were a lot of uncertainties in it and a lot of controversy about it, but he planted the idea of dark matter in the consciousness of astronomers and astrophysicists working in the decades that followed. And he did a lot of work to lay the groundwork for the idea of dark matter. And then Vera Rubin worked with a collaborator. She worked closely with this man named Ken Ford, who basically designed and built this new technology that really dramatically improved how well cameras worked. So another interesting theme in my talk is that Henrietta Swan Leavitt's participation in astronomy was made possible by an advance in photographic technology. And anytime there's like a huge change in how the technology works, it kind of shakes things up and lets new people get involved. Like all the old ways of doing things don't really work anymore. And so, or aren't the best way to do it anymore. So new people can get their foot in the door and get involved. And I just thought this was interesting too, that her collaborator, Kent Ford, built this better technology. And then she was able to use that to get better pictures of galaxies and make these amazing discoveries. So in both cases, it was specifically the advancement of cameras and photography that allowed these women to make these amazing discoveries. Sort of interesting. Okay, so let's talk about what she discovered. I said she was famous for studying galactic rotation curves, which are some of the primary evidence for dark matter. And I can walk you through how it works really, really quickly and easily. You probably heard that Mercury is the closest planet to the sun. And if you don't know, Mercury goes around the sun really, really fast. It just takes a few months. It travels, oh, I've got a table here. It travels at this tremendously fast speed of 48 kilometers per second. Now Pluto got demoted. It's no longer a major planet, but we still got Neptune out there. And Pluto's still out there too. It doesn't care that it's been demoted. But anyway, we've got Neptune out here. Neptune is the farthest major planet from the sun. It's 30 times farther from the sun than the Earth is. And because the sun's gravity is so weak out where Neptune is, Neptune actually goes around the sun very slowly. So it turns out that, you know, the sun is what causes, it has this gravitational pull that pulls on all the planets in the solar system and causes them to orbit around it fast if they're close to the sun and slow if they're far away from the sun. And the reason I'm telling you this is because I'm going to talk about this concept of a rotation curve and what it means for dark matter. But I think it's nice to start by looking at like what a rotation curve is and really understanding that. So here's a diagram of, it's a lot easier than it seems to follow. Here's a diagram of a rotation curve for the solar system. And the farther to the left a point is on the graph, the closer it is to the sun. The farther to the right is, the farther it is from the sun. The higher up a point is, the faster it's going. So all that means is that Mercury, way high up, this is Mercury, it's right next to the sun. So it goes really, really fast in its orbit around the sun. Neptune is far away from the sun. It's way down low on the graph. That means it goes really, really slow in its orbit around the sun. This is the normal way we expect things to behave. If there's a big, massive object like the sun, sort of centrally located and everything's going around that, then the things that are far away should go slow and the things that are close should go fast. And that's what people expected to happen when we started to look at galaxies. Remember, galaxies are huge neighborhoods of billions of stars, but they're really bright at the middle and they're much fainter around the edges. So you'd expect that when you look at a galaxy, the things that are close to the middle, where all the mass looks like it's concentrated, there's like billions of stars in the middle of a galaxy and all this gas. You'd expect it, just like Mercury goes fast around the sun, you'd expect that things that are close to the middle of the galaxy would go really fast, and things that are far away from the middle of the galaxy would go really slow, kind of like this shape here. But what Vera Rubin discovered by looking at about 60 different galaxies is that each one of them had a rotation curve that looked like this, like curve B here, instead of curve A. And what this means is that stars and gas, they're way far away from the middle of the galaxy, like hardly even looking like they're part of the galaxy. Things that are far away from the middle actually orbit around the center of the galaxy just as fast as things that are right near the center, which was really weird because that doesn't seem to obey the laws of physics. If all the mass is concentrated at the middle of the galaxy and you got a star that's like 100,000 light years away from the middle of the galaxy, it ought to go really, really slow because the gravity should be so weak, but it doesn't. The stars at the edge of galaxies go just as fast as the stars at the middle. And it's not just one galaxy. Here's an actual picture of a galaxy, and here's the rotation curve for that galaxy. In this particular one, the stars at the edge go even faster than the ones in the middle. That would be like Neptune, just like zooming around the sun super fast, and then Mercury moving really sluggishly. It seems to defy the laws of physics. And here's rotation curves for a whole bunch of other galaxies too. So the only logical conclusion that people have come to is that it must not be the case that all the matter is concentrated at the middle. It must be that all around here, there's some kind of invisible matter that's pulling on the stars around the edge of the galaxy and causing them to go faster. And that's what we call today dark matter. Now, there are other lines of evidence for dark matter. It seems really, really likely, although we have not yet identified what dark matter is, there's so much strong, compelling evidence for its existence based on how things move, like galactic rotation curves and other lines of evidence too, that most astronomers are pretty convinced that dark matter is real. In fact, not only is dark matter real, but there's about 6 times more dark matter than there is normal matter, like atoms. Like atoms make up planet Earth, your body, the air we breathe, stars that we can see, all the bright stuff in the Milky Way galaxy, all the gas in between stars, that's all atoms. And that's about 4.6% of the matter and energy that make up the universe. And there's about 6 times more of the dark matter. Then I don't want to go too much into this because we could do a whole talk about dark energy as well, but the universe seems to be accelerating its expansion. And we don't even know what's causing that to happen. So we call whatever force it is that's causing the universe to expand at an ever and ever more rapid pace, dark energy, meaning it's just an energy source that we don't really know where it comes from. So when we talked about Henrietta Swan Leavitt, our first fantastic woman tonight, she forever changed our view of how big the universe is and how far away things are. And then Vera Rubin forever changed our view of what the universe is. Like, it's not just atoms, it's dark matter too, and how much dark matter there is. So these are 2 completely fundamental shifts in our understanding of the universe that were both made by these incredible women. So that's why those 2 are just incredibly inspirational to me. Now, I noticed when I was reading through and researching Vera Rubin for this talk, I found something that was an echo of what Henrietta Swan Leavitt experienced. Rubin was a observational astronomer, right? She observed galaxies and took really meticulous data and then made conclusions based on that data. The majority of the people who would judge articles that were going to be published in scientific journals, they often would demand that she not include any interpretation of what the data meant. Her interpretation that there was dark matter causing these rotation curves to behave the way they did, people were very skeptical of it. Dark matter was a difficult idea. It's still, even today, a difficult idea to accept. We don't like to deal with so much uncertainty about something so fundamental as what the universe is made of, right? It doesn't feel good not to know what that is. So there was a lot of skepticism of her ideas, and people went so far as to demand that, if you want us to publish your work, we want you to just give us the numbers, just give us the data. We don't want to hear what you think it means. And it was like painful for me to read that, because it was such an echo of what happened to Henrietta Swan Leavitt. Edward Pickering said basically, like, it's not your job to interpret what any of this means. It's your job to write down the stars, like write down where they are, make a list. And it was kind of the same sort of attitude. But this did not deter her. She stood her ground. She continued presenting her research, and today she is revered as just an amazing scientist who made incredible discoveries. And as part of her legacy, there is a gigantic telescope being named after her, the Vera Rubin Observatory. Now, Vera Rubin was never awarded the Nobel Prize. And that, in a lot of people's estimation, that was an absolute travesty. She should have gotten the Nobel Prize for the magnitude of discoveries that she made. And unfortunately, she passed away in 2016, and the Nobel Prize is never awarded posthumously. It's always only awarded to living scientists. So she now will never get the chance to receive a Nobel Prize. But as an astronomer, I would much rather have a big old huge telescope named after me than get a weird medal. So I think this is an amazing tribute to her. And personally, I actually traveled, this telescope's in Chile. Actually, I should show you where it's at. Here's South America, Argentina, Chile. It's up in the mountains in Chile. It's there's a telescope as part of the observatory called the LSST, and it's going to be looking at a huge area of the sky. There's the full moon, just for scale. It's really unusual for telescopes to photograph this much of the sky all at once. They're usually way more zoomed in, like on one of these squares, or zoomed in even more than that. So this telescope is going to be able to take like 15-second exposure pictures and just scan across the sky and take pictures of like everything in the observable universe over the course of a couple of nights. And it's just going to be absolutely amazing. It's 8 meters in diameter, which is huge. It's like 30 feet across almost. So it's an incredible telescope. And personally, I was able to travel up while it was under construction and see it. And it wasn't named after Vera Rubin yet at the time, but I was so pumped to see this telescope. I went on an expedition to Chile in 2019 as part of the Astronomy in Chile Educational Ambassador Program. And I wanted to just share with you, it's only about 30 seconds long here. I'll play you a clip. This was my journey in a bus going up to the observatory, and you can see it, just zoomed away. You can see it under construction up on the hill. They do have on the left-hand side of the road in Chile. So I was pretty frightened. You can see we're not on the left. I'm sorry, they drive on the right-hand side of the road. We are not on the right-hand side of the road. So I was scared to death that a car was going to come around this corner and that would be the end of my life, which is why I stopped filming at that point. But we did make it up the hill, and I was able to see the Vera Rubin telescope under construction there. I was so excited when we went on this expedition because, oh my God, I'm going to get to see this telescope. But it turns out in Chile, they don't like to allow random interlopers from the United States to just wander around expensive construction sites. So they didn't actually let us go in there. Right from where this is actually the Gemini telescope, if you've heard of that in the background. But from where I was standing, I zoomed in as much as I could, And I got to see this telescope that's going to be, this whole observatory is named after Vera Rubin, under construction. And it was just so cool to get to be there and see a little piece of it as it was being built. Okay, so that's going to be a phenomenal legacy for Vera Rubin. I have just a few minutes left to tell you about my last very special woman. Now, she is not as famous as the other two that I've talked about, but she is just so personally inspirational to me. And so I wanted to share about her work. Kathy Vivas is a Venezuelan astrophysicist. I was lucky enough to meet her when I went on my trip to Chile a few years ago. She has a PhD from Yale University. And her main focus in her research is she studies RR Lyrae stars, which are really, really similar to Cepheids. They're just a little smaller and they pulse a little faster. But the whole idea about them is basically the same. They grow and shrink, they're signposts. You can use them to measure the distance to other galaxies. Now, she uses them to study the neighborhood right around the Milky Way. It turns out that there are dozens of these little tiny dwarf galaxies that are sort of hangers-on around the Milky Way and orbit around us. And by mapping out where they're located exactly and precisely, we can build this dynamic map of how gas is flowing through our local neighborhood and how the Milky Way galaxy, we can learn how the Milky Way galaxy formed and what its future is going to be based on collisions of other galaxies with us that might have happened in the past or might happen in the future. And basically she's leading the charge on projects that help us to map out our own neighborhood and see what the history of the Milky Way galaxy is, which is so exciting to me. So instrumental in understanding the structure of our galactic home, our galactic neighborhood. This is the telescope where she works at. And I took this picture on my trip and I thought it was nice because these two little smudgy objects that you can barely see are the small Magellanic Cloud and the large Magellanic Cloud, which are the places where our first woman, Henrietta Swan Leavitt, found all those thousands of variable stars in the past. So I was actually able to see those. You can't see them from Santa Rosa, unfortunately. They're only visible in the Southern Hemisphere. So if you go to Chile or Australia or New Zealand, then you can go see the Magellanic Clouds, but they're a little trickier to see around here. Inside of this telescope dome, there's this gigantic telescope. It's the 4 meter. 4 meter refers to the diameter of the telescope. There's actually a giant mirror under this white cover. The cover's just there to protect it. So what happens at night is they open up the roof of the dome, they take that cover off, there's a big old mirror there, and then light comes in from space, hits that mirror, and then gets focused by this curved mirror into that giant black thing. This is actually an enormous camera called DE-CAM, which stands for Dark Energy Camera. And this is the biggest camera I've ever seen. And DE-CAM is what Kathy Vivas uses to do her work. So again, just like the first two women I highlighted, were able to do their work because of advances in photography. That same thing holds true again. Kathy Vivas is able to use this enormous camera to discover all these really faint variable stars in galaxies that are close to the Milky Way. And here's a picture. This was published just less than a month ago. So in February, Kathy Vivas discovered over 300 pulsating variable stars in a little tiny galaxy called Antlia 2. And each one of these little red dots is an RR Lyrae star, which is just like a Cepheid variable. And I love this picture because this is the modern day version of this, right? Henrietta Swan Leavitt had to painstakingly look at all these photographs and manually mark all of the stars on them and say, okay, here's a variable star, mark them all down. Kathy Vivas's work is very different. She uses this enormous freaking camera to measure these stars, but then to actually discover whether they really are variable stars or whether there was just some like disturbance in the atmosphere that caused them to dim out and rule all that out and make sure she's really discovered variable stars. It's a tremendous amount of work. You can look up this article from last month and read through it. It's just phenomenally complicated. I love it. But I just wanted to show you that connection because this is what's so inspirational to me. Kathy Vivas is carrying on the exact same sort of work that Henrietta Swan Leavitt did. So Henrietta Swan Leavitt made discoveries that enabled men who came after her to make their own discoveries based on her work. Vera Rubin used discoveries that have been made by men, like Fritz Zwicky and her collaborator who built that camera. She based her work on their work in the past. And then we come full circle. Kathy Vivas is now a woman carrying on work from a woman in the past. And I just love that women have been involved in such a real way in astronomy for so long that now we have this kind of like multi-generational passing of the flame, passing of the torch, carrying on the work from one generation to the next. And personally, I'm very appreciative of Kathy's work because she actually shared her data. After I met her in Chile, she shared her data with me and helped me to write a lab activity that I use in my classes based on her research. And I have my students actually look at our Lyrae stars and real data that Kathy discovered and actually measure the distance to stars in other galaxies. So I'm trying to pass that torch on even one more step to my students today. All right, I want to thank you so much for listening, and I hope you found something in this talk that will stick with you. And if anyone has questions or if there's more that you would like to know, I'd be happy to stick around and answer questions.
Oh my gosh, thank you so much. That was really cool, very, very interesting. And we did, I think, have a couple, where is it now? Sorry. My chat seemed to have disappeared. Oh, okay, here we go. So Chuck asked, how did Henrietta get access to photographs from the Southern Hemisphere?
That is a great question. You know, I'm not sure which observatories those photographs were coming from. And nobody's ever asked me that before, and it's a pretty obvious question. So you know what, I don't know. I know that they were building observatories in Chile in the 60s and the 70s, but I don't know how early there were telescopes located there prior to that. So I'm not sure if they would have come from Australia or South America. I don't know, but I'm going to look it up later and find out because that's a really good question.
And there were some comments, fantastic name for the Hubble Space Telescope that you suggested that it should have been called after Henrietta.
Oh, thank you.
Another person said that may be the best description of how dark matter acts upon matter that we know of. Colleen asked, back in Henrietta's day, how was she able to distinguish Cepheids from other kinds of variable stars?
Great question. She was able to construct, so there's a type of graph that we call a light curve. And a light curve is basically just a graph of how bright a star is versus time. And when you construct a light curve of a Cepheid variable, it has a sort of particular shape to it versus other kinds of variable stars, like you know, another type of star that can vary its brightness is an eclipsing binary star. And I know Colleen knows what this is, but for everyone else that's listening, eclipsing binaries are pairs of stars that kind of orbit with one in front of the other. And when that's happening, when the brighter star goes behind the dimmer star, it causes the whole thing to look dimmer. And you can't see the two stars individually with the naked eye, or usually even with the telescope. They're so close together, they just look like one star. But when one goes behind the other, it causes the star to dim out. So when you look at that and actually graph it out and create a light curve for it, that has a really particular shape to it. It's like everything's normal and the light curve is flat. And then when the eclipse happens, it goes down. And then when the eclipse is over, it goes right back up and flattens out again. So that would be, if you saw a light curve that looked like that, that would tell you, oh, this variable star is probably an eclipsing binary star. But if your light curve kind of has more of like a sawtooth pattern where it comes up and then dips down and then back up again and dips down like a sawtooth shape, that's kind of a characteristic of an RR Lyrae star. And then Cepheid variables have even a slightly different shape. So it's by looking at the shape of the light curve, I think, is the primary way that they would distinguish what kind of variable star that you're seeing.
Great, great. Also just curious, you may have mentioned that, but the that 4-meter Blanco telescope that Kathy Viva uses, where is that?
That is located in, it's at what's called CTIO, Cerro Tololo Inter-American Observatory. It's just a little ways away from, I'm going to pull up a picture and show you kind of where it is. Oh, I've lost my button to share my screen. Let me share my screen again. So going back to this picture of, here I am up here. Okay, so this mountain is called Cerro Pachon, and that's where Gemini and the Vera Rubin Observatory are located. This person who's standing here, the direction they're looking, you could just, I don't have a picture of it here, but you can just barely see CTIO, the other observatory where the Blanco telescope is. You can see it from here. And when we were here on this day, this was at about 4:30 p.m. And they said, okay, we're going to drive over to CTIO, which is the other observatory. And we're going to do it tonight. And we got to go before it gets too dark because the road is really scary. And there's like this really, I wish I had a picture to show you right now, but there's this really winding road that went down the side of this mountain and then back up the next mountain. And the Blanco telescope is just over on that next mountain. And we had a kind of a harrowing drive that took about an hour to get over. It's not very far, but the road was just so windy. It took us a little while to get over to it. So it's in the same area in Chile, basically.
Interesting. Well, that's a lot of observatories in a small,
Yeah.
in one area. Must be great skies. All right. Sorry, going back to the questions. Danielle asked, can you remind us how Leavitt changed our understanding of the universe? You said it so concisely.
Sure. She changed our understanding of the universe to where before Hubble's work that was based on her discovery, before that, we thought that the Milky Way was the entire universe. And so we thought that maybe the universe was 100,000 light years across, and that was it. And then after that, now the Milky Way is just one galaxy out of 100 billion. And that's a pretty big shift because you're changing from this is our whole universe to this is just one out of 100 billion galaxies. It's a massive change in our understanding of the size of the universe. And I see Art actually. Hi, Art. Great to see you. So glad you're here. You went to Chile with me. I haven't seen you since then. But he had an answer for us about where they got the photographic plates. Harvard had telescopes in Peru and South Africa. And those telescopes provided the plates that Henrietta worked on. Thank you, Art, for saving me there.
And then Zachary asked, great lecture. I wanted to ask about efforts to map the MWG and other close galaxies like the local group and where we could look at those star maps.
Great question. I have, if you want to get in touch with me offline, I have some videos that I could send you. There have been amazing visualizations done where they've taken 3-dimensional data of the location of all these different galaxies and flows of matter through the space between galaxies and just mapped it in kind of 3 dimensions. And it's just visually stunning. So let me actually, any of you who have questions can feel free to email me. There's my email address in the chat. And yeah, if you email me and just remind me, I will send you some video links that you can see. Yeah.
Awesome. A lot of thank yous and excellent lecture and inspiring. I don't think I see any other questions. Yes, more thank yous, thank yous. Does anybody else have any more questions for Laura before we end here? Okay, I don't think so. Yes, lots of thank yous, as you can see.
Well, thank you to all of you. I'm so appreciative that you took the time. I know we're all busy, so to take the time to come out here and learn about and honor some of the women in astronomy, I really appreciate you coming.
Well, it was wonderful, so interesting and inspiring and fantastic. So thank you so much for your time. especially to you, Laura. We so appreciate it. And hopefully you can speak for us again sometime in the future.
Sure, I'd love to.
All right. Thank you, everybody. Thanks so much for your time and have a good night.
Thank you.
Bye.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Art, how are you doing?
Hi, Laura. Doing great. It's good to see
Hi.
you again. Yes.
Yeah, great to see you.
I really enjoyed your presentation. Thanks again.